Ok, mamá, no podemos abrir a la puerta. No podemos perder comida, pero es muy importante. No, el lobo es peligroso. Tiene unos dientes y unas patas y que quiere comérselos, pero es peligroso. ¿Vale? Ok, mamá.
For example, you can initialize a hash set by using previously initialized list by passing it to the instrument. You could create a hash set with no parameters.
Del abuelo.
You can also specify particular
Pero después vamos a ir a la casa de su hermana. Pero yo voy a ir yo sola. Adiós.
And there's also this ability to set up the load factor. The default load factor is not 75. Why do we need the load factor? Why do we care, right? Well, you see, the hash set checks, like any other set, checks the uniqueness of what you're actually adding to the set. So you cannot add the same element to the set hash set twice. It's not allowed. Now, there is an implication here. In order to check the uniqueness, you have to basically look at the elements that are already in that set, right? Well, in a small size set, that's not a problem. But as the hash set will grow and you will start adding more and more elements to it, to check the uniqueness, to check that the new element you're adding does not overlap with anything that is in that set already, you would have to deal with larger and larger set of elements, and eventually your performance will start to degrade. So it will degrade with the growth of the set, which is not good. So can we improve that? And apparently hash set has a built-in algorithm which is actually trying to improve it. And the algorithm is based on the idea that every element that is based in the set, that's placed in the set, is added to kind of a bucket, to a segment of elements. And the set is subdivided into multiple such segments, into multiple buckets. And the elements are grouped into these buckets based on their hash codes. So all elements, all objects that are added to the set with certain similar hash codes are in one bucket, then another group of objects with different hash codes in a different bucket. And that means when the hash set accepts an element that you're trying to add to, it only needs to get its hash code, it only needs to check one of the buckets, the one which is in the range of that hash code. It doesn't really need to scroll through the entire hash set to validate if this element occurs or not. It's enough for it to just check subset. So it's much quicker, obviously, and more scalable approach. But then, for performance reasons, to reduce screen as you start adding more and more elements, there is a subset of the bucket within a set grows over a certain capacity. So you more than 70 entries are already added. Then at that stage, the hash set will just create an additional bucket to accept more elements. So we'll not fill every bucket to capacity. We will kind of leave space within every sort of internal group of object storages to accept extra objects that may fall into that range of hash codes that is the basis of it. It's an automatic process. It's not like you have to code it. Hash set already has the relevant elements. It's just for you to appreciate what exactly it's trying to do and why there is this low factor. So you can basically specify how full you want internal storage of the set to get before the set starts reshuffling the buckets and optimizing that storage. So say for example before the 75%, I'm saying actually allowed to up to the 80%. Okay, so these are the ways of creating hash sets. One more set off. Yeah? which creates a read set, very similar to the list which we created read. Now, let's take a look at the operations we perform in this set. So operations allow us to insert, delete elements, check existence. Again, let's just zoom in and play around with this example. So we first react upon the same premise that we have a few objects which we allocate into memory food, breathe, and another. 3 points basically. So cake, love. Now we create the actual set, and again, you could specify the size, but default is 16 elements. And we're saying that we're using generics, we'll accept any products to be added to that set. And just like with the list, we probably would like to use the interface name. Maybe we change our mind and instead of hash set later on decide to use another type of set implementation. Right? So we wouldn't have to include anything because anyway, so we create that hash set, and by default, remember, it creates a capacity, storage capacity for 16 elements. Well, it didn't specify the size, so default is 16, and I'm not drawing all the 16 elements. And their values are not yet set, so I haven't added actually. Now let's start adding them. So, just add. And then we add an element, another one, another element, and so on. Yeah? So just simply call the method add. Oh, well, that's interesting. We add in the same element twice. So what's going to happen in this case? Well, actually, nothing. Except that this method add Boolean indicator of true or false, which indicates whenever it actually added something or not. So if the add method returns false, you know that it actually ignored whatever you just tried to do, right? And why would it ignore it? Because the element p2 is already present in that collection. So it's not going to put it again to set checks in the mix. And the next thing we do, we add another element p3, and this one will actually be added, of course, because that's not yet present in that particular collection. Now, what about remove? Sure, we can do that. Remove a particular element, and we'll search through and remove that element. Okay, and what else we could do? We could remove. How strange that is. Well, again, it just returns you Boolean. If it has nothing to remove, then you won't remove anything, and it has something to remove, well, then you know what it just removed. So there's also a method contains, which you can invoke, and that basically tells you true or false whenever the certain element is or is not present in that set. So we've looked at the way we set content. Right? Now let's take a look at the deck, array deck. Just create this double-ended queue where we can add and remove things from top or bottom of the queue. Again, the way of creating array decks, you can create an array deck with no parameters that creates a deck of 16 elements, where you can specify capacity, and it expands if required automatically, and you can populate array deck using the contents of another collection, for example, using a list, right? Set, whatever you want. So, now how do we manipulate with array decks? Okay, there's several algorithms that are available here, and again, let's zoom in and take a look at this. But basically, they implement first in, first out, or last in, first out. But let's take a look. The example here again assumes we have a couple of products that we allocate, cake, tea, cookie, whatever, just some products, and then we create deck object, array deck object to store these products. And again, it creates an array deck of 16 elements. Draw all the elements. That's basically it. Now let's take a look at if we'll just try to get something from the array deck, and there's nothing in there. Well, if you just try to do the poll and get the element, then you'll just get null if there's nothing inside. Okay, that's nothing particularly exciting. What will happen if we try to add elements? There are two ways of adding. You can offer an element first. That will add it to the head of the deck. So let's say we call the offer first and we put the cake there, right? Now we call offer first again. What's going to happen is that the cake will be moved to the next position. And on the first position, well, we added something else. We added so we actually kind of shifted the contents of the deck forward, and we added something to the top. That's the first one. Now, when you then try to get values, you can do the poll first. Gets the first element from the head of the deck and actually removes it from the deck. So that will be gone, and then the contents will shift forward, and the first element of the deck, whichever element was previously second, will become first. You can grab the element from the deck without actually removing it. That's the peak first element. That allows you to get the first element, but not physically remove it. The poll will remove it. Now, the next thing you could do is offer last. That allows you to add things to the tail of the deck. So let's say offer last, and that adds it to the last position just after the last valid element that was in the deck. So offering the element there, and again you can keep offering, and what will happen is that further elements will be added behind last position. And guess what? There is the option of poll first. There is an ability to poll last, and that will remove the last element, return it to you, and remove the last element. Okay? And use also peak last, and then allows you to look at
Una
without
niña
actually
joven que apenas está comenzando a vivir. ¿Cómo está cansada, bebé? ¿Corriste mucho?
Sí,
Entonces necesitas vitaminas. Vitaminas de cambur. Uno solo, toma.
There you go, that's how the array deck works. So with array decks, we can do first out, the last first out algorithms, generally treated as a flexible way, adding next, hash map. Hash map is a combination of two collections. It's like a table of two columns, which stores key value pairs.
Voy a
You
cocinar.
can construct a hash map with more construction, which creates a map of 60 elements, which is you can specify capacity. You can also specify another hash map. Grab items. And also you have this method of, which creates a map that specifies the entries could be value, next comma, next key, comma, next value, or these key value pairs could be wrapped up into the object called map entry. So you can do it that way. So it's not alt entries that allows you first to group key value pairs into entries before you add them. There's a slightly further advantage as well. Entries versus okay, so yeah, overlap operates. Now, how do we manipulate with maps? Okay, so we can include, remove, get elements, to check existence of elements within them. Again, let's zoom into this example and observe how it actually works. In this scenario, we're looking at a pair of columns again, K and T, and then we're allocating a map, a hash map, And notice that this map is using two key, which is and the second one is value, which is the integer. Let's assume that we're storing something like products and their quantity, like the order. Yeah? So, for example, the products will be but it's important to understand that the key is actually a set, so that means it's unique, right? And well, the value is just a list, so we can add the same quantity to different products if you like, but you cannot duplicate. Anyway, so you've allocated this hash map. By default, it comes as a map of 16 entries because I didn't specify the size in the constructor, but it will expand as necessary. And well, there are no values in that map yet, so let's start adding something. And when we add values, we basically just say what it is that we want to add, product P1, P2, and the integer, but in this case, yeah, value of 2. Strictly speaking, I should draw here instead of the actual number 2. I should draw the arrow from here pointing to another chunk of memory because integer is not included, it's wrapper class, so it's not in the heap yet. But just to sort of declutter the graphics, I'm just drawing here the number 2. So in fact, you need to realize it's a reference to the integer object rather than a primitive. Yeah, because you cannot use primitives with collection API, because you have to use objects. Anyway, so we've added some entries into the map. What will happen if we'll just try to put value for an existing element? So this P1 already exists in the map, right? But now we put in 5 instead of 2. Well, that will act as an update state. So that value of 2 will be replaced with 5. Put actually returns that and 1, you know what it was there in this value of 2. So it's an update, but you can find out what was the previous value that you actually updated. So that put method returns. Of course, if you try to remove something, well, then the entire entry will be gone. So you're removing the product 2, which is that T, which is this entry, right? And it will be just gone. Okay, what if we will try to check if something is or isn't in the map? Do we have the product P2 in that map contains key P2? Well, not anymore. We just removed it, so that has T of variable will be false. Contains key method will return false. You could also so contains value method, and you can look for something that has a value of, well, in this case, 1 is 2, right? And again, it's no longer present. It will be value of 5, we'll just update it. Right? Okay, and what about this example? What if we try to get something? Right? What do we actually get? If you say get me P1, which is a cake, you're not actually getting cake. No. You're getting the quantity, which is 5 in this case. Okay? That's how the hash map is used. Right? Let's keep that there. Right, so next one, we're looking at the way in which we can iterate through collections. Several examples. The first example is array list, and it's pretty straightforward. You add some content to it, and then you can just use it in the for each loop. It's as simple as that. You could use any collection in the for each loop because they all implement iterable interfaces. So if you use hash set, array list, whatever you want, DAG, you could just iterate. Now, you could use this technique. Out of the collection, you can get an iterator object. And the iterator object has a method called hasNext, which basically checks if the next element exists or not, and you can put it inside a while loop, for example. because it returns you boolean, true or false. Next element exists, it returns you true. If it doesn't exist, it returns you false. The method next allows you to retrieve the next element, and you keep iterating. You can also remove values using iterate. When it comes to the hash map, you've got a choice here. You may get a set of keys out of it and iterate through the set of keys, or you can get a collection of values and iterate through a collection of values, or whichever way you want. So for example, the first example here gets the set of keys, and then for every key in the map, which is keys, you can get the actual quantity. You can get whatever quantity is stored in. And the second example, you just get all the quantities and you ignore what the keys are. Yeah? For example, if you want to compute something like a total, yeah? You don't really need the keys in this case, you can just get the values. So as you can see, the for each works nicely, and if you want to do a little bit more sort of advanced coding, then I guess you can use iterator instead of for each. That's how you iterate.